In this exercise, we will be examining the BLAST tool. BLAST is the basic local alignment search tool and allows to take a sequence and search in a large database to find sequences that are related or homologous to the sequence that you provide. Our starting point for doing the search is the National Center of Biotechnology Information. This is the homepage of the NCBI, and under Popular Resources we find the BLAST tool. This is the interface of the tool, and we have different type of blasts according to our needs, from the basic type of blast for nucleotide and protein sequences and the translate version of these searches, and also the specialized blast for particular type of searches. In this first example, we are going to search for a unknown human protein sequence. So we have to select protein blast. This is the interface of the protein blast search. First, we need to enter our query sequence. We could paste it, or also you can upload a file. The second step is to choose the database used for the comparison. These are the available database for blast search of protein sequences. We have a non-redundant protein sequences in the National Center of Biotechnology Information, reference proteins, the UniProt database, and other database for proteins. Let's go to select reference proteins. Then we have to select the algorithm to perform the search. We have different options of different algorithms. In this case, we are going to select a protein-protein basic blast search. Also, you can modify the parameters like the number of results that you want to obtain for the search, the threshold or expectancy value that you want to obtain, the word size that in case of protein could be 3 or 2 word size letters, and also the scoring parameters like the type of substitution matrix that we're going to employ for doing the search, or the penalties for the opening and extension of gaps. We're going to keep the default parameters and do the blast search. Here is the result of our search. The first is the graphical display that shows all the hits, and you can navigate to these lines and discover who are the sequences. Here, for a first visual analysis, we already see that we have a number of high score hits which almost cover entirely the query sequence length. Then we have the hit list, when the results are organized by the score or expectancy value. Here we have a group of hits with very low expectancy values, which indicates strong evidence of evolutionary relationship. Also, there is high values of identities. In this case, our first hit is shared 100% of identity of our query sequence and correspond to the hemoglobin subunit alpha of Homo sapiens. As you can see, all these results are hemoglobins from different organisms, and our first hit is the hemoglobin of human. Here we have the alignment, the values for identities and similarities between the sequences, the gaps in case of they exist, and if you can see in the alignment, the middle row indicates the similarity between the two sequences. If they are similar, there is a letter that corresponds to the match character. In case that there is no similarity, it could be a blank space or could be a positive sign. In this case, is indicative that these two residues share common physicochemical properties, so they are similar and they're going to be included in the calculation of positive residues. Another important aspect in the blast search that could be useful is this edit and resume button. If you want to change parameters or modify something, you can go to this button and return to the original submission page. Let's now going to do another type of search. We can move in this region between the different type of blast. In this case, now we are going to use a nucleotide blast. So we eliminate the sequence of the protein and we going to use an unknown sequence of nucleotides. You can copy and paste in a similar way, and for the case of nucleotides we also have to select the database. That in the case of nucleotide we have all these options. In this case we're going to maintain the nucleotide collection database, but we can change according to our needs. Also the selection of the type of program that we want, and the algorithm parameters that in the case of nucleotide sequences there are modifications with regard to proteins, like the word size that in nucleotides are larger than for proteins, and the scoring parameters that use different metrics for computing the match and mismatch characters. In the case of proteins are the protein substitution matrix. In the case of nucleotides, it will be changed to another matrix. Then we can do BLAST, and these are our results. Here we have the hit list, and according to our results, the first sequences has an e-value of 0, which means that are almost the same, and all correspond to the influenza A virus nucleotide sequence. Here we can observe the different alignments between the sequences. And here there is an important point. When we see this kind of alignments between very similar sequences that has minor changes, sometimes it's useful to locate these small changes, and this graphic display is not the best way to do it. So we can go to the formatting options and modify parameters. Instead of use as alignment view pairwise vision, we can use this kind of vision, which means that when you find an identity, instead of putting a letter, you place a dot. Let's go to reformat our alignment to see how it looks. Here is the resulting alignment after the formatting. Here we can see that it's different than in the first case. We have our query in the first row, and there is 60 characters length, and then the rest of the hits in subsequent rows. Every time that there is a coincidence between the query and the hit, instead of putting a letter, the program puts a dot. So it's very easy in this type of view to observe the changes that occur between our query and the other sequences in the database. This is a more useful view for detect small changes between highly similar sequences when we see a BLAST result. These are the basic uses of BLAST for protein and nucleotide sequences.